For our next speaker, we have Marynel Vázquez. She's the assistant professor of computer science at Yale University and the head of the Yale Interactive Machines Group, where she's an awesome researcher doing social robot interaction. So with that, let's welcome her.
All right. So thank you so much for waiting until the last presentation today. I know you're probably very tired and want to go home. And so what I want to do is I want to talk about sort of navigation from a more human perspective. And by the way, a lot of the work that I'm going to be presenting today is actually work that Nathan over here has led. He's graduating very soon. And so thanks to Nathan for doing all this hard work. And so let me start with this paper that a bunch of us worked on a while back. This is a sort of basically an effort, a community effort to think about all the things that are happening in navigation and where things are going. And I want to bring up the most awesome figure I have ever had in a paper that was actually made by Anthony over here. And the reason why I want to point this out is because I want to show you that there's a lot of things that we care about in navigation. And despite all of us coming together as a community, agreeing all these things matter, I have sort of very, very sad news. And that is that I still don't know what is the best approach for social robot navigation. Isn't that kind of, it makes me very sad, you should know. And the reason why we don't know is not that we haven't tried. We have actually tried a lot, but it is very hard to know because what matters depends on the context. And we care about robots navigating in many different contexts. And so just to make this a little bit more concrete, I wanted to bring up this short paper that we wrote a couple of years back, which was basically a set of interviews of people that work in social navigation, mostly in industry, although a few people were from academia. And what we did here was we told them, hey, we have all this set of metrics that matter for navigation, one of them being collisions. Can you rank them for the problem that you're working on related to social navigation? And pretty much people agreed, hey, collisions, those are bad. We want safety, right? This is very obvious. Number one thing that we care about. But then when we ask them about all these other things that we agree, seem to matter, I mean, it's just a whole mess, right? and this is what actually makes really, really hard understanding what's going on, how far have we gone, right? And so in my perspective, I think because it is so hard, we need some kind of standard platforms to measure success. And a lot of people, including us, have been working on simulation for this because it's very easy, right? To change the way that you're computing your metric and saying, oh, okay, if I care more about this, how is the ranking of the algorithms, right? And so because of that, we basically spent a number of years, and this is again, Nathan's lots of years, sort of developing this simulation environment that now is pretty much open source. You guys can use it. And so I just want to advertise it very briefly in case you're not aware of it. The second version of the simulation environment, which is the more recent one, the whole motivation for this was that, look, we have an environment with people in it, and we want people to effectively move in a way such that they're going to induce a particular type of social context, like maybe people navigating down a path with a robot, or maybe people coming together as a group. And it just happened that for us, it was really hard to control people in a way that once you start the simulation and people move, they actually do what we intentionally sort of wanted to see happening in that simulation originally. And so a lot of what is sort of embedded into the simulator are tools to help you define how people are going to navigate, with the goal that once you start and you click play, then things hopefully will start looking in the way that you intended in terms of how people navigate nearby a robot or what they're doing nearby a robot. Here in particular, this is implemented with the Unity interface, which makes it kind of easy to define this graph through which people are going to move through. And then the nodes, you can see there's two colors, there's pink and purple nodes, because some of them are just waypoints for people, but then others are locations where you want to see group formations coming up. Now, the nice thing of all of this is that this is integrated with ROS. And so if you're developing your algorithm, right, with the standard ROS framework, then you can actually test it and put it together into the simulator. Now, for a number of years, we've been sort of trying to motivate people to use the simulator. It's not perfect, but there's no perfect simulator. We just want to make progress on sort of measuring, right, where we are. And I'm happy to report that at least a number of people have paid attention to us, which is great news. And so if you're looking for a simulator that has people in it, that other people are using, that you can hack, that is open source, then I encourage you to at least take a look at this particular option. Now, the rest of the time that I'm going to be talking today, I really want to focus on this question of how do we know if the robot is doing a good thing? So in past talks, we've heard people say, oh, well, what is it that people care about? It's all here. It's in their brain. How do we know what exactly are they thinking? And I want to suggest that perhaps now we're starting to get tools that can get us to answer a little bit of that question. And so what I'm going to present now, most of it appeared in this paper that was published recently. This is work that was done also in collaboration with Chipping, which is another one of my students, and then also researchers at Google DeepMind. And so the main idea here is we want to scale how we can, in a way, measure from a human perspective how well a robot is doing. And so to do this, we said, well, okay, we have a simulator. Can we use human reactions to a robot in that simulator to then predict what are they thinking of the robot? Is it navigating in a competent way? Is it navigating in a surprising way? Is it navigating in an intuitive way? We consider all those 3 dimensions. And we started using simulation for this because we can actually equip someone with a head tracking device so we can actually get all the time continuously their facial reactions, which is much harder, obviously, in the real world where perhaps the person goes out of view and things like that. And so in this particular data collection, the goal is for the person to follow a robot in a warehouse, which you can see there in the computer. And as they're doing this, we're sort of tracking the position of their avatar. They have, that embodied sort of human in the simulator that corresponds to them. And then every once in a while, we ask them, hey, what do you think of the robot? Again, in terms of these 3 dimensions. So this is kind of like a typical survey. It just happens in the simulation right there as people are doing things. The nice thing of using the simulation, of course, is that you can freeze time, right? And whatever is happening, you can just continue after you've finished asking people what they think. And so I'm going to show you here sort of 3 different ways in which we looked at this data. One way was by looking at the spatial behavior of the agents in the context of that physical environment. And so this is a rendering of basically the locality of the robot as he was navigating. Here, the robot is in blue. And then the person that was following the robot is in red. This is the person that had the device on them. And then all the other arrows are other people that were navigating nearby. And then green is the goal that the robot is going towards. And so what we did was we said, okay, this is one way in which we can visualize the data. This is probably close to how the robot is looking at the world. How well can people predict what that person, the follower, was thinking of the robot if they look at this data? Okay. Now, we also asked, what if people, instead of looking at this data, were looking at how the person was reacting to the robot? And we also said, oh no, that video is not playing. Let me try it. Let's see. Yeah, you can get it there. So this is a recreation of the facial movements that we got from that VR device, right? And so we were asking, what if I show a human this video and ask them, what is that person thinking of the robot? How well can people predict this? And then the third thing we tried is, well, let's show people everything. And so we allow them to see both this spatial rendering and then the human face. And so let me show you how well people did at this task. So on the y-axis, you have F1 scores, so higher is better. And then I'm going to show you 3 bars, one corresponding to only seeing facial features, only navigation features, and then all the features together. And so for competence, navigation features and all features were much better than only facial features. And similarly, we got a similar result for surprise and intention. Now, just to contextualize these results, this black line is what you would get if you try to do a random baseline. So clearly, people are at least telling us, hey, there's some information in that data that you got, right? It may not be perfect, but there's some information in that data that you got that actually allows to make a prediction about what people may be thinking. Of course, we're not at an F1 score of 1, but it seems like there's some useful information there. And so then we said, okay, well, let's now use machine learning to see how well we can do this task. And here we tried a multi-layer perceptron transformer, a GNN, and a random forest. And here in particular, we use all the features because that seemed to be beneficial based on the human performance. And so here you can see now the results again. Funny thing, we're all believers in deep learning, right? But it turns out my small old-style random forest did much better in this task. And this should not be surprising, right? We don't have that much data. Like, we ended up collecting data from, I think it was like about 60 people. And even though that is reasonable for HRI, it's not a small data set for HRI standards. It's actually very little data for deep learning to make sense of all these different things. Now, for context, this is again the human baseline that we had before. And so it seems like machine learning could potentially be used for this task, right? There's some promising results. Now, we also then went to the real world and said, can we actually do this with a real robot, right? And we kind of emulated the procedure that we use in simulation, where now we have a person that is following a robot, that's the person in black. And then at some point, the robot said, pause. Light turned red, and then we actually asked the person, hey, can you fill out the survey now in this mobile device? And then they continued the task. And so now we had sort of more real world data that we can use for this type of problem. And so here's the results that we got now using that specific data for test, where we either trained using real data or, of course, a separate different partition, or data that we got from the simulation, where we actually adapted the simulation to make the observations a little bit more similar to what we could actually get in the real world. So like, for instance, before we had full observability around the robot, here we had a more limited set of field of view. And so overall, it seemed like using real data is slightly better. But nevertheless, it was quite surprising to me, at least, to see that with VR data, we could approximate it reasonably well. And so that's kind of exciting in my opinion, because obviously getting VR data is much easier in general than doing this in the real world. And so just to summarize quickly the key takeaways from this paper, the first thing I want to mention is that I think there's a lot of promise of using these machine learning models to infer internal unobservable variables that matter for navigation. And perhaps this is an interesting way to expand how we evaluate performance. And also, importantly, for this particular domain, for the task that we tried where a robot was following a person, it seemed like the spatial behavior was a lot more useful than the facial features from the person. It may be that this was because, well, there was some noise in the way that we were capturing the facial expressions. But nevertheless, this is very practical, because getting those facial expressions in the real world is really hard. Because again, the robot is moving, the person is moving, and oftentimes their face is going to be occluded. Now, more recently, we have experimenting with large models, because, we're all wondering, will they solve this task? And I want to present some preliminary results. We haven't published this at all, but I think it's kind of exciting to test this idea. What if we were to use a large model for this task? Here in particular, we're using a large language model, not a visual language model, because when we actually try to start this, visual language models didn't actually work very well. But you can imagine that in the future, perhaps that would be very, very useful for this kind of problem. And so I'm going to show you results with 4 different types of prompts, where the first one, the blue one, limited task, limited feature, means that we provided a featureized version of the data as a puzzle to the LLM. You may be like, what? Well, we wanted to make sure that the LLM was making sense of the task in the way that, you would naturally expect. And so this has the very bare minimum information that you need to make a prediction, where this is almost as if I pass the data to my random forest that doesn't have any semantic understanding. So, here's features, here's my label, and this is in context learning. So we pass a couple of examples. Can you make a prediction on a new test example? Now, the other way we tried this, which is now the 4th row, detailed task, detailed feature, is we actually explain the task and then we explain the features, which is what you would expect. And then we had a combination of these 2 things where the orange bar, detailed task, limited feature, is we provide information about the task at the beginning, but then the features are very uninformative, if you wish, and then sort of the opposite of that. And then we compare this with a random forest, because that seemed to be the best in our prior results. And so here's the results that you get with only 4 examples of data. Here, note that I've switched to accuracy. This is not directly comparable to the prior results that I show you, because we actually partition the data differently, and I can expand on that if you have questions why. But just to say, again, higher is better. And for the most part, passing information about the task and explaining the features actually turn out to be useful. And this is clearly much better than a random forest, right? Like the performance that we're getting is actually making it practical for use. Now, this is what you get if you actually try 64 examples. Just for context, 64 examples for some models ends up being a problem, but right now with models like Gemini that have a really long context, then this is okay. And here, of course, random forest does much better, but still we see potential of using large models for this task, which is kind of exciting in my opinion. And so I'm going to end here, and I'm just going to reiterate this idea that I think the simulations can be useful. They're not necessarily the end goal. But if you combine simulations with novel methodologies to capture human perceptions of robots, perhaps we can start measuring, how well these robots are doing in the real world in a more user-centered perspective than we have been able to do that before. So thank you so much.